Okay, so I'll cut to the chase. Try to make up for some of the time. So, a bit of background. So this guy over here, Nafio, was is now a big shot neuroscientist, but back in the day in grad school, he was my ramen and coke friend. So I went to have ramen and cokes every Friday after working hard the rest of the week. Well, he still is my ramen coke friend. So a few years back, he told me that he's got super cool data about brain activity. It's a unique data set in the world because he's managed to convince the right people to be able to report the brain activity of patients before they undergo certain type of surgery. Well, and then they play some economic decision-making games, and he's able to get access to that data, to report that data. So one of the only data sets in the world of these characteristics. So he told me, hey, I have this problem, and can you maybe help me to analyze this data? And I said, yeah, sure. Do this, that, easy. And then it took us 4 years. It turns out there were a bunch of problems along the way that we sort of figured out eventually. So Michele is a senior co-author. Arnold did some of the work. He did his PhD at UC Irvine, and that's me. They did most of it. Okay, so anyway, the story really is in principle very simple, and then there was going to be some nuances. So the story is simple. It's just I want to figure out which covariates X affect are truly associated to an outcome. Y, standard variable selection. That's it. With one nuance is that I'm also given certain coordinates, certain z's, and I'm not interested so much in learning about whether a variable affects globally Y everywhere, but I want to learn about when at which coordinates there is an effect. So it's local variable selection. Let me give you a couple of examples to motivate what this is about. So example number one is some salary data set. The outcome is the log of the hourly salary that a person gets. There's a bunch of covariates. Here's 6 of them. There's others not being shown. What I have here is age, so the age of the worker. And I'm looking at the effect of these covariates at different ages that means different career stages. Okay, so here in 20 are people who just entered joined the workforce, and then here 60 are people who are close to retiring. And you can see here 6 different covariates. So for example, and on the y-axis what we have is the posterior probability using the non-division framework that the covariate has an effect on salary. So for example, over here, with this panel, what we have is the posterior probability that the black race is associated with log hourly salary at different ages. And what this evidence suggests is that this association is present most of the time. So there's a negative salary gap for being black, or for being a woman. There's a positive, there's a surplus, positive gap of association with going to college, for example. But for example, for people who just entered the job market, this difference is not, it's not big. Okay, it doesn't look that big. Okay, so these are posterior probabilities. This is how likely it is in the Bayesian sense that there's an effect of these covariates at different coordinates. So Z is H in this example. And then these are estimates of the covariate effects. Okay, so that's one example. Another example, the one that motivated this whole work, is this brain imaging data. What you have on the left is brain activity reporting. So these patients were doing it, they were playing certain games, 200 rounds of the same game, and they had to place bets. And sometimes they won, sometimes they lost, or different types of rewards that they do. And so, for example, this is showing like the average brain activation over the games in which a particular patient won and when that patient lost in a particular location of the brain. And so what we see is at time 0, but for time 0, the guy is placing the bets. At time 0, the outcome of the experiment is revealed. So he or she knows whether there was money being won or lost. And about half a second afterwards, we see some difference in brain activation. The person wins, then boom, part of the brain activates. Yeah. And so that's on the left. On the right, what we have is the probability, the posterior probability that a bunch of different gain covariates have an effect at different moments in time. So you can see that most of the covariates, there's no evidence that they have an effect, except for this covariate called regret, and this covariate whether the gain was won or lost. Yeah. So again, it's a local variable selection problem because we want to learn whether covariates have an effect, but the specific coordinate in this case given by time. Okay. Hopefully that helps fix the ideas. The challenges are that I'm going to let the outcome depend non-parametrically on Z. Okay, that's what we're seeing in this brain activation example, certainly. And then we view Z as the input gene. So it's not like time series where we have discrete grid over time, but we view this as a continuous one. Okay. In example number 1, I could view the data as independent, whereas in example number 2, this is functional data, and I'll have to deal with that somehow. Also, I want to consider that potentially there's many axes, so it's a high-dimensional variable selection exercise. And then here, I could naturally start considering non-parametric methods. The issue is that we would probably need a larger sample size to deal with this non-parametrically. So what we consider doing is a semi-parametric method that I'll explain in a second. Also because it's easy to interpret, computation gets easier. And again, so for a very large number of covariates, then with lesser sample size, you hope to be able to do a good job. Okay, so we're going to go semi-parametric. Since I don't have much time, I'll just summarize this slide by saying that if we do a critical issue here, it's going to be that the model is misspecified. Right, like of course, as data analysts, we build a probability model or some data analysis algorithm that's supposed to capture the nature of the data, but that's never going to be accepted. It's right. So there's going to be always some amount of misspecification. And in standard settings, a bit of misspecification is not too bad. So all of these like classical results telling you that both in frequentist and Bayesian frameworks, you can kind of recover the truth of the optimal parameter values with enough data, etc. A main message from this story is that for local hypothesis tests, for local variable selection, actually, because of misspecification, the type 1 error of hypothesis tests can go to 1 and then goes to infinity. So you're sure to have false positive rules. So it's a severe problem caused by model misspecification that doesn't happen elsewhere. And this is regardless of being Bayesian or frequentist. It's a problem in the likelihood, it's not a problem of putting a parameter. Yeah. Let me give you guys an example that with this, I think that's enough to get the intuition of what's going wrong. So on the left, so this is a simulation exercise. On the left, this is a setting, a simple setting. There's just one binary covariate defined in 2 groups. And so I have in gray are the 2 group means. So truly, up to 0, there's no difference between the 2 groups, the average. After time 0, there is an effect of this covariate. Okay. Now, of course, I don't know what these gray guys are. So I'm going to use some sort of class of functions to approximate this. In this case, I'm using splines, cubic splines. I could be using Gaussian processes or favorite non-parametric or semi-parametric tool. But then what happens is that what the black lines represent is the projection of the true expectations of the guys in gray on the spline basis. That's the best possible approximation I can hope to obtain as n goes to infinity. So even with an infinite amount of data, the solution converges to this black lines. And the issue is that these black lines, see, they're ever so slightly different in here. Even though the gray lines are equal, there's no covariant effect for z less than 0. In here, because the model is misspecified, actually there are some differences. So you might think, well, this is tiny. That's a moderate practice, yeah? Well, so here's on the right, I'm giving you the posterior probability that there is an effect of this covariate. In gray is for a standard Bayesian variable selection exercise that one might come up with. And in dashed black is the variation that we proposed. And you see what's going on is that this gray guy is basically pretty sure, in the Bayesian sense it's completely sure, that there's group differences in this interval where there truly are no group differences. If you use p-values, it's even worse. Yeah, p-value is 10 to the minus 15%. Okay? So they have very strong evidence. Okay. Now, of course, if you guys should start complaining now and say, well, look, yeah, but you know, this is a splines. What I'm showing you here, the black dots are knots. And if you were to add more knots, then you expect this effect to diminish. So maybe it's no longer an issue, right? The issue is that however you replace the knots, then this can behave so this issue is highly less sensitive to how you place the knots. And a priori you don't know how to place them. Okay. Also, if you place too many knots, the sample size between these intervals gets too small and you have no power to detect that. It's not so easy to calculate. Another possibility would be to use trees, things something like random forest or BART on the Bayesian side. That we have a bunch of experiments showing that even though that's okay for estimation, controlling type 1 error there is not straightforward. So in some simple example, we find type 1 errors are around 81%, which is higher than what we would normally have. Okay. I'm not saying that this cannot be done by putting more knots. I'm not saying that this cannot be done by using trees. I'm just saying that it's not straightforward. I would love to see these papers, but this is not our paper. Okay, we're doing something else. What we're doing is we're going to use a semi-parametric model. It's going to be very similar to using splines, but we're going to use a notion of something called a cut orthogonal basis. And the selling features is that regardless of how you place the knots, you're protected against false positives. Okay, so as a statistician that really takes to heart the hypothesis testing business, I don't want to have false positives, I'm going to control that. Okay, regardless of how I place the knots. We're going to then propose, and this is going to be valid whether you're requiring this derivation. We're then going to propose a multi-resolution analysis that's going to help us improve power, and it's there that the Bayesian framework really kicks in. Then we propose high-dimensional theory that we're going to recover the right model and things like that as Engels definitive, as allowing for the model to be specified, we propose some computations, and again we consider independent and functional data, and Z would be multivariate. So in the example that I just showed you, Z was univariate. But I have here some, I'll skip this for the sake of time, but this is an example where Z is bivariate, and the summary of this example is just to say that the same thing happens. So we should be seeing zeros, there's some simulation setting, different sample sizes, and on the right bottom corner here, we should be seeing zeros, there's really no effect, and that's what we see for every sample size. Yeah. So we see that we don't have type 1 errors. And then whenever there's truly an effect of the covariate, then we get numbers converging to 1, meaning that we have statistical power with the differences whether we are. So I'll skip the bivariate settings just for time, but very interesting afterwards. Okay, so how do we formalize this? Okay, so let me go slowly. This slide this is an important one. So okay, so you know the data generating distribution by F. In principle, it could be anything. And then the data generating expectation, right? So the expected value of the outcome, given the covariates and the coordinates. I'm going to write it in this particular way. So of course, this is a conditional expectation. It's just a function of x and z. So it's of course just a function of x and z. So I could make do with just having f1 in here. The reason why I add f0 is because I want to be able to interpret f0 as the baseline as the average value of the outcome. And then I want to be able to interpret F1 as deviations from that baseline mean. And to do that, I need to place some up to zero identifiability constraints on F1. Okay, so for any value of Z, the effects of X add up to zero. Okay, but if you take this, then the problem that I'm posing is local node variable selection. So it boils down to simply this, no? So if I want to see whether the J covariate has an effect at a particular coordinate Z, this is just asking on whether this F1 at this given Z depends on Xij. That's it. It's simply that. Okay. Now this is the truth. And now next is the model that I'm going to be assuming to do data analysis. And in this talk is a frequently variable. Yeah, with the truth on that. So my assumed model is going to assume that this is going to show expectation given by data. These are model parameters. That's given by some data node that depends the principal non-parametrically on Z, and then some covariate effects. So note, this is a standard linear regression. It's just that the coefficients in the linear regression are allowed to depend on Z. This is a classical object case with dictionary called the very coefficient. Okay, so that's the basis here. So what I'm doing is I'm assuming that the covariates have additive effect that was not present in F1, but now I make an assumption of additivity to make interpretation easier, inference gain statistical power, etc. Yeah. Of course, I cannot leave it at that. So what I'm going to do then is I'm going to restrict attention to a certain class of functions, of betas. This could be in principle anything. It could be spline, it could be used, it could be Gaussian processes, it could be something. But the key of the story is that basically you have some basis for this space of functions. So that's what I'm calling W. So W now is this space is the basis for this space of functions. And then this beta node and this beta one is given just by a linear combination of spaces. And the weights of this linear combination, the betas are our parameters. Okay, so that's what we do, the betas. The W's are given functions, we have to learn the betas. I'll show you, if you've never seen this kind of thing, I'll walk you through the basics in the next slide. But just staying in this slide for a couple more moments, if the question know that the question is that whether this beta local variable selection says whether the effect of covariate J at a particular Z is zero, but this is just asking whether this guy is zero in red. And since this guy in red is equal to this linear function of parameters, right? Doing variable selection locally amounts to testing whether the linear combination of the parameters is equal to zero. And that's something that we know how to do, right? We know how to test for linear combination of parameters. So I've made a potentially complicated problem. I turn it into a much simpler problem. I've linearized the problem, and then I'm just looking for zeros in linear combination of parameters. Okay. Again, if you've never seen these lines, let me show you the introductory slide I give to students when I'm teaching these things. So here's an example where beta 1 of Z, so shown here, right, is obtained by adding 5 W's, the weights given to each of these W's, these are these coefficients, betas, so the model parameters. And the W's look like this, yeah, so this is a so-called linear B-spline basis. And you can kind of see that since each of these W's is piecewise linear, then their sum must be piecewise linear, and it also happens to be continuous, so it is a linear B-spline. Okay, so we get something like this, piecewise linear and continuous. Now, the beauty of using linear B-splines is that it makes the local variable selection exercise a bit simpler, because see, if I want to test whether beta is zero in this particular interval, yeah, from 0 to 1/3, this interval here. Well, since all of these W's, there's only 2 of these W's that are non-zero, in this particular interval, right? The other three are exactly zero. So if eta 1 and eta 2 are equal to 0, then the sum of these two guys is 0, and therefore beta is also equal to 0. Okay? So what this has done is that by using these splines now, to test for local variable effects, all I need to do is to test for 0 in parameters. Not linear combinations in the parameters, just zeros in parameters. That's it. Now this is standard variable selection. Right? We're going to regress the outcome on the W's, look for zeros in the parameters. That's it. That's all we need. Okay. Now let me talk a bit about model misspecification and how do we get to prove that the strategy is going to be consistent. Going to consistently select only the local effects as time grows. Okay, so what I've said so far amounts to saying this, that I'm assuming this model, so I'm going to take a Gaussian model. So the in vector notation, the vector y is a Gaussian with the mean given by the W's and the etas. W naught is the basis for the baseline, so say cubic splines, and W1 is the basis for the local convergence. Now, most parameter estimates that are reasonable, they converge to some optimal parameter, eta star. This eta star, if you want to say it in a fancy way, is the projection of the true expectation on the assumed basis on the W's. Yeah. So formally, the Gaussian case this, and if you look at the last line of this expression, this is saying that the optimal parameter values are going to be obtained by regressing the data, the true mean on the W's. That's it. And the issue that in general, these eta stars are not going to contain zeros. Even if there's truly no covariate effect at a particular set, in general, you can't guarantee that this is going to have zeros. So your Bayesian solution, your frequentist method, whatever it is that you use, as time grows, going to be converging to a non-zero parameter estimate, and therefore you may claim that there's an effect that will distance. So what we would like to be able to do is to modify the problem in a way such that two things happen. First is that this asymptotic eta star is guaranteed to contain zeros in the right places. First thing. And second thing I need to prove is that the database procedure is going to convert to the asymptotic. Got it. Yeah, so these are the two pieces. So for the first piece, look at the asymptotic solution contains zeros. What we use would be called an orthogonal cat basis. It's perhaps a fancy name for something that's really very simple. So if you spend some time thinking about this, it's really something very simple. So the idea is that suppose that we split the set into regions. Yeah, like H, split H into chunks. Yeah. For now, given, although we'll do a multi-resolution analysis to learn that. The idea is that we're going to set a basis W, since that satisfies two properties, basically. The first is that the entries in the asymptotic parameter value coding for a local covariate effect are only associated to one region. I'll make this a bit more explicit in the next slide. Yeah, that will be called a cat basis. And second is that there's certain orthogonality conditions in these W. So that's why orthogonal and cat. Let me maybe make this a bit clearer. I think this maybe expression over here makes it clearer. So W is the basis for the baseline, beta naught. W1 is the baseline, is the basis for the covariate effects. So we have a certain number of regions, this guy here. And then an orthogonal cat basis is defined in the following way. W0 is whatever. And then W1, what you have is this, that the idea is that first we're putting the observations in region number 1, then region number 2, then region number 3. So it's a cat basis because see, this region is coding for local covariate effects in region 1 is 0 everywhere outside region 1. Okay, so this basis is only non-zero within this particular region. Everywhere else, it's going to be zero. And likewise for the other. Yeah, so that's what we call a cut basis. It only has support on a given region. And also within some orthogonality condition that is W11 is uncorrelated with this guy, W12 is uncorrelated with this guy, so on and so forth. Now this is something that is simple to do because all you need to do is, for example, if you were going to use splines, for example, or GPs, whatever it is, for local covariate effects, all you need to do is, first of all, truncate that basis, set it to 0 outside of the region of interest, and then regress it on the baseline and take the residuals. That's it. Now, so these residuals are orthogonal to the baseline value. That's it. That's all. Right? So it is something very easy to do in practice. Okay. So then there's this lemma that then, if you look at the optimal, the asymptotic solution of the optimal parameter value, eta 1b for region B, which contains the estimated effects for the P covariates. So this vector is obtained now by taking the design matrix in that region, to do the linear regression of the expectation in that region on the design matrix in that region. It is easy to show because of orthogonality. The general expression we had before can be proven to be this in 2 lines. Yeah. So in words, what this means is that the optimal parameter value is found by regressing the true mean on these local effects, and therefore, if this true mean is linearly independent of a covariate, given the other covariate, so there is no local effect, well then it follows that this guy is equal, right? So this is exactly what this is for linear association. So this is telling us that the asymptotic solution will have zeros, and that when there's a local covariate effect is not present, we're gonna have a zero in this zero star. Okay, so we're in good shape. Okay, I'll skip this for the sake of time. There's a similar argument that can be made for functional data. There's some extra nuances in modeling the dependence, but I'll skip that for the sake of time. Okay, so now the rest is kind of embarrassingly simple. So again, I'm assuming this model, this Gaussian, canonical Gaussian model, etas are the parameters. To do local variable selection, I want to test for zeros in eta 1, but now this is totally standard variable selection. You could put lasso, whatever you like, we use basic models. Okay, so we set up some priors on the models and the coefficients. This is not our main. For lack of time, I won't go into the details of these priors and whatever. They're standard things in the literature. So we took our standard stuff out of the box, applied it to this model. And the beauty is that then you can get things like the posterior probability of a model. And in particular, the posterior probability that this gamma JB is an indicator for this eta 1 JB quantifies the local effect of covariate J in region B. Okay, so you can get the posterior probability that this covariate effect is local covariate effect is non-zero, given the data, using the standard Bayesian formulas. And all of this can be done in standard ways. We use MCMC, you can use your favorite software packages. Priors, I'm gonna skip it. I'm happy to take questions afterwards if you want, but I'll try that choose. Up to this point, there was no need whatsoever of the equation. We have done this with penalized likelihood, we use p-values, whatever. Yeah. Now, the multi-resolution analysis bit is one place where the equation comes quite naturally. So the idea is as follows. Up to now, I've been assuming that you have the coordinates and that you somehow chop them into pre-specified regions. in practice, you don't know what this region should be. Right? And the way how we think about this is that in most practical applications, so for example, in the salary data, economists don't care. If you look at intervals that are narrower than say 5 years or 2.5 years, they don't care about that. They don't expect the effect of any policy to avoid gender gaps in salary to have an effect in less than 2 years. So don't care about that. In the brain experiments, it takes a bit of time for the brain to process the words and whatever. So there's a certain amount of milliseconds that's the most you care about, narrower than that. So the idea is that is the highest possible resolution in your analysis, and it's dictated by practical considerations about the problem. So in this case, the highest possible resolution I might care about are nine regions. Yeah. But the idea is, okay, I could do this, but power might suck. Like I would be protected against that one. But power might suck because if I don't have enough data within each of these intervals, intuitively I'm not going to be able to assess covariate effects in these intervals very precisely. In a situation where covariate effects are similar across regions, then maybe what I want to do is define coarser regions, so lesser resolution. Yeah? So that's what we call multi-resolution analysis. So we have, in this case, 3 resolutions. There's the finer resolution, an intermediate one, and then a coarser resolution. And what we'd like to do is somehow learn from the data which of the resolutions is the right one, and take into account also uncertainty in choosing the resolution. Okay? And this is very natural to do in innovation model averaging framework. Let me check on the time. Okay, I will briefly mention this then. So we have L resolutions in general. Each resolution has an associated set of regions, like the previous slide, associated parameters and models. Overall, across all possible resolutions, the probability that the covariate J has an effect Z is obtained just using the local probability as the weighted average of the posterior probabilities in each resolution times the posterior probability for that resolution. So this is vanilla, a standard Bayesian model. Yeah, totally standard stuff. And in fact, the beauty is that computationally we can even run computations in parallel for each possible resolution, and then just combine the results afterwards. Computationally, it's not super costly to have multiple resolutions. Okay. Let me maybe say a few words about the theory on this, and then that'll be except for a couple examples. So the theory is what I want to do is so eta 1 star is asymptotic parameter value that is guaranteed to contain zeros when there are no covariate effects. This gamma is an indicator, this guy is 0. And what we would like to show is that as the sample size goes to infinity, the posterior probability assigned to the correct model, meaning the one that's the correct configuration of local effects as it corresponds to the truth, that converges to 1. In this case, we prove L1 convergence. And I'll explain why. We give convergence, we give the associated rates, we account for model misspecification, and there's a bunch of nice properties that come out of this. In particular, that the probability 1 and grows when we're covering the right set of local effects. If I care about estimating effects, also that the Bayesian model averaging posterior disaggregate here converges in distribution to the oracle that corresponds to the model, to the posterior end of the model that knows what covariate effects are for them. And there's also arguments that you can actually also prove you must have found the probability of frequentist errors, type 1 errors, type 2 errors. So we have frequentist guarantees on uncertainty quantification guarantees from these L1 thing. There's some assumptions that we made. One is that F, the data only include F is test adoption tails. These can be relaxed with the effect mostly the rates. There's some data mean conditions on how small the two parameter values can be. That's standard in high dimensions. There's sparsity conditions on the size of gamma stars, so many parameters are truly non-zero. Again, a standard condition, and then standard conditions on the prior not being too sparse or too non-sparse. So more or less standard conditions in the data. So let me briefly mention the group strategy, not because necessarily I care too much about groups, but this is a group strategy that has been very helpful to me in several papers when it came to variable selection in high dimensions. And so let me just take you through the main idea, because we see that it's quite simple and clean. So L1 convergence just means that if I add up the posterior probability assigned to all of the wrong models, that in expectation, that its expectation leads to converge to zero. By definition, now, the expectation of a sum is not expectations. Now, if you use a space formula, the posterior probability is T of gamma given Y is the posterior probability of a model. It can be written as the marginality of the data given the model, and the model probability divided by the normalizing constant. This can be written in this way. So up to here is all totally trivial. And then this step is just upper bounding this term by removing terms in the denominator. All the terms in the denominator are positive, and if I remove some of them, I'm just making the quantity larger. And the idea is that this term here, the posterior probability of a model, is comparing the value of a model with the value of all of the other possible models. What I'm doing is, no. I'm just going to compare the value of this model divided by itself and the true model. And I'm going to discard everything else. It turns out that this bound is tagged. Okay? Whenever there's posterior concentration of the true model, these bounds can be shown to be tagged. So you don't lose much by thinking this room. Okay, so that's the first step of the proof. And then the rest conceptually is very easy because see, this guy over here is a positive random variable. So its expectation is obtained by integrating its survival function, that right probability function. And so I just, if I can bound these tail probabilities, I can bound this expectation. And notice that the only thing that's random in this quantity over here is this ratio of marginal likelihoods under the true model divided by the competing model. That's called the base factor. Okay, so all you need to do is to be able to bound tail probabilities for base factors. You can do that, you can bound this term. If you can bound this term, you bound this guy, and then you just need to, by bounding each individual term, you also bound the sum. You need to do some nasty summations and things, but conceptually, this is all that's going on. It's a finite end result. There's no syntactics application. I'm just saying, this is strictly less than or equal. So any bound that you found, fine, strictly bound the probability of this the expectation. And in this case, it's not too hard because these factors effectively involve quadratic forms of subcalculation and random variables, for which there's lots of results. I think I need to stop in 5 minutes. So if I have a couple of minutes, then I'll walk you through at least one or two of the examples. Okay, so this first example is a simulation exercise. It's just showing kind of what I've been saying in words. So there's 10 covariates. Covariate 1 has an effect. The other covariates don't. Covariates are correlated. And here is the power, so the proportion of simulations in which we claim that there is a local covariate effect at different coordinates. Our method is the green guy, so you can see it's making no mistakes for z less than 0, and this is the region where there truly is an effect. And when there truly is an effect, well, sometimes we pick it up, sometimes we don't, depending on how strong the effect size is. For n equals 100, for n equals 1000, then you get a perfect reconstruction. The guy in red is what would happen with the standard line, so we're not using these type of nominal beasts. So there's false positive inflation, as you can see, for any 100, also for 1000. And then in blue is this VC bar, so a random tree, basically based alternative. You can see how this guy is rejecting the null, like here about 15% of the times when it's really should. And even as the sample size is super large, if you're 1000, then you still get even worse. Yeah. Okay, so this is showing that there's false positive inflation, and even worse, the false positive inflation may not even happen near the boundaries where the tree is an effect to an effect. It will happen anywhere. Here for trees, it happens quite far away. So you're claiming that there's effect for z equals -3, even though the covariance only has an effect for z greater than 0, which that's a serious mistake. Okay. Now, just to, I'll finish up with this example. So this is again this salary data thing. I guess the main thing that I want to emphasize is that the multi-resolution analysis here we consider two resolutions. One that defines 5-year bins, the other that defines 2.5-year bins. And then this is the results that I already walked you guys through. So for example, it's obvious that there's always, at any age, there's an effect of quality education, positive. There's a negative association with gender. There's no association with the environment employed or self-employed. And with racial issues like being Black or Hispanic, there's an effect, but not immediately after joining the workforce. This is the picture that we get with the multi-resolution analysis. Suppose for a second that we don't do a multi-resolution analysis, and I say, no, look guys, I don't want to have 2.5-year bins. I want more resolution. I want to say 1-year bins or 1.5. So like I want a more precise picture of what's going on. So this is a result of doing the exact same analysis, the exact same methodology, but now using 3 times as many nodes. I've been claiming throughout that can cause columns of power. Here you can see clearly that one. So for college education, we still find an evidence for an effect most of the time. For gender, we're starting to lose some power. Government and self-employed, we get the same picture as before. But look for the Black race. According to this analysis, there's no evidence that the Black race has an association with salary at any career stage, whereas here it's super clear. And in fact, if you do a like silly least square type analysis, you find p-values that are 10 to the minus sources. They don't have stems. Yeah? So clearly there is an effect over here. But if you subdivide, you go too non-parametric in some sense, then you pay the price. So this is where it really pays off to the evaluation. Yeah, I think I already sort of walked you guys through this very imaging example. So yeah, I think I've said most of these things. I'm out of time, so I'll just mention that if you are interested in these things, there's software in this R package on the app. And then these are the main references. This is the main reference on this paper. And these are 2 papers with Javier here on Bayesian variable selection on under misspecified models that may be relevant. And this last paper is a Bayesian analysis paper where I outline this framework to study high-dimensional consistency of model selection. In Bayesian frameworks and frameworks where we use Angelo criteria, BIC, EBIC, and things like that. Okay. More time.
Thank you, David. Are there any questions?
Thank you for the talk. Just on the BMA point and the multi-resolution analysis. So in that last example, you only needed 2 archetypal resolutions, 2.5 and 5 years.
For the salary.
For the salary. In general, can you get away with so few archetypes, or how many different resolutions can you look at? And then going beyond that, is there an ambition or possibility to make that continuous, so beyond the discrete number of resolutions and having some continuous prior and posterior over your resolution.
Right, okay. Okay, so in principle, yes, you can add as many resolution levels as you want, but computation is next year. Also, you can have next year because it's longer.
Sure.
And also effectively what you're doing is a search for possible models. And the number of possible models increases exponentially with the number of discretizations that you use. So the narrower the intervals, the larger the model space that you use. So in principle, yes, and in principle, if a final resolution is not needed, the few probabilities on the resolution should tell you so. So effectively, you would end up discarding that, but computations will get a bit higher. Now, in terms of making it continuous, that's a very good question. I am not sure that that is possible. We could not come up with a way how to make it fully continuous, because whenever you make it continuous, you start having this situation where the estimated group differences here depend on the optimal value, and asymptotically depend on the estimated group differences elsewhere.
So you remove the orthogonal assumption.
Right. So you need to somehow make it such that it's completely right. So it's continuous, but somehow there's an orthogonality across regions, so that the parameter estimates here don't affect the parameter estimates here. So if there is a group effect here, you will not wrongly infer that there's a group effect on the adjacent interval or another interval. Okay. So we have to figure out a way how to do that. We couldn't figure out that. So that's why we thought the multi-resolution analysis was sort of like a reasonable way how to do it, because see, this is discretized, this is discretized, this is discretized, but then if you average across these different discretizations, you're getting a smoother option.
Sure.
It's a bit like a random forest versus a single tree. No? So you're smoothing things a little bit. But I was not able to figure out a way how to do it. Maybe it's possible. If we figure out the way, I would have to. So I really thought about it. Any other questions?
I guess kind of the same, not the same, but almost the same question. Are you restricted to equispace
No.
grids?
No.
Do you have some other? Is there some other good strategy for searching this?
Yeah, that's a very good question. So okay, so we didn't do anything fancy.
If you want to get close to the change point, basically, right?
Exactly.
Do exactly like the space. You're changing it all over the place, like the sort of block.
But in principle, the machinery that we discussed can be applied to any partition that you consider. And so can the multi-resolution analysis. So in principle, yes, you could specify many different types of these ways how to distribute the points and then learn that, but that wouldn't be very efficient computation.
You need some nice priors. Problem is that
I suppose, yes, you would need to place some kind of prior on the node locations.
Yeah.
Right? And then somehow that perhaps encourages some clustering across interesting regions where the function changes more rapidly. If you wanted to be very pragmatic and forget about being fully Bayesian principle for a second, we kind of run analysis like this, forget any other analysis that gives you a rough estimate how the function behaves, and where it changes more rapidly, it plays more knobs.
Yeah.
Right? Now it's empirical based, so it's forbidden some people that we probably would put it for simplicity. But yeah, I don't know. Maybe I would have to place knobs randomly one way or the other. And there's literature on these things, right? So for any given number of knobs, there's literature on doing node selection and placing them. So even so, it is doable. It's not unlike again, it's not unlike trees, for example. No, yeah, you could probably borrow from literature. That's a very good thought.
Is there maybe something in between? Because here you're doing your model averaging across each resolution. But there could be regions where the high resolution is better and regions where the low resolution. So you could do that model averaging conditionally on your Z
Yes,
to get
exactly.
some in between.
Yes, that's, yes, totally. Well, yeah, I think you would need a similar strategy there. Like, okay, in principle, yes, because you would have, I call them resolutions, but really there is a set of nodes. So you could have one set of nodes that's uniformly spaced, and another set of nodes that's uniformly spaced here, but denser in another region of Z. Then you average across those, and ultimately you get more resolution in one place than the other. So you could try to play around with ideas like this, yeah, like partitioning. Yeah, that's.
I would say more in the averaging. You fit it with 3 resolutions, and then you just don't average by weighting resolution L given Y, but you do L given YZ somehow. Do you see what I mean?
Yeah, but from like from standard Bayesian model averaging, you can't really do this because if you're conditioning on each resolution, each set of nodes, and then the weights are given by the overall weights, not the local version of those weights. So I think you would end up having to, maybe you have this resolution, and then the next resolution is say has twice is the same up to Z up to here. Then from here to here you have twice as many nodes, and then here maybe you have twice as many nodes up to here, and then less resolution here. So you would have to go. Well, that's one way how to play. I don't know if there's a better one. But honestly, allowing the random distribution of the nodes and learning that sounds like we just discussed. That sounds way simpler.
You could do a kind of cross-validation or something, right? If you get outside of standard BMA, you go to kind of generalized BMA, then you probably have more room to do local kind of things, and now people develop like efficient methods, right, for kind of calculating cross-validation from MCMC output. I don't know. But yeah, people have kind of come up with methods at least for that and how effective some of those are.
Sure. So if you expand the set of models, if you're willing to consider, or averagers to consider this, and then you somehow calibrate it predictably or something like that, that is totally possible. I'm not 100% sure. Like, you would need to still be able to prove that somehow you're guaranteed to recover the truth, which is not immediately obvious here, because for this, you know that with enough data, you're going to pick up one resolution, whichever one is closest in detail, divergent, whatever. And for that resolution, you have the theory telling us that the consistently recover right now. If you start calibrating things predictably, you need some extra layers with groups, which maybe can be done. And I don't see why not, but certainly we need, yeah. Well, yeah, no, great. I agree. So, something to think about.
Okay, then we can put the seminar here, and we can continue the discussion. So thank you again, David, for coming.
So then we will do these things when the referee asks. Thank you guys.
Thank you, Lauren.
Yeah. Okay.
Just a quick question on the last.
Hotel to the seminar, he's coming from BPF, and we will talk about some topics on variable selection.
Okay. Super, thank you, Javier, and thank you guys for being here.